3.3, we were looking at increasing and decreasing functions and the first derivative test. And if you'll remember, the first derivative test talked about when you have increasing and decreasing functions, how all of that relates back to derivatives specifically when we're talking about increasing and decreasing. And then maximums and minimums we also talked about as well, though we haven't had a problem that actually asked us to find one yet from this perspective. All right, so we had done this example. We had talked about using this process, and the way that we have done that is we took the derivative, we set it equal to 0 and does not exist to find our critical points, and then we created a sign chart for critical points and tested values in between them to decide, do I have a derivative that's positive? If so, it's an increasing piece. Do I have a derivative that's negative? If so, it's a decreasing piece. And if we have any locations where the derivative is constant or 0, it's a constant piece. That's not your typical thing to have happen. The increasing and decreasing typically are, okay? We also talked about the fact that if we change from increasing to decreasing, we have a relative max. And if we change from decreasing to increasing, we have a relative min. So we're on to a new example. I mentioned when we did this example that a lot of these, in fact, most of them are not going to be intervals given, right? There's no interval given, like we had when we were looking at absolute extrema. The exception to that are trig functions. The reason that there are intervals given on trig functions is that they have this oscillating pattern, right? So think sine and cosine, where it keeps bouncing up and down, which would mean you'd have infinitely many maxes and mins, infinitely many increasings, infinitely many decreasings. And it isn't so much that we couldn't identify intervals still in that fashion. It's more about the process that it's sort of overkill for what we're trying to accomplish here. Right? You do that in trig. You identify in trig like every single location where it has a maximum, or maybe every single location on a tangent function where it has an asymptote. You do that in trig. It's just not what our focus is for this content. So you will see on trig functions typically an interval given that we're looking in between. And while it's not always 0 to 2 pi, it often is, because 0 to 2 pi indicates, when we're dealing with sine and cosine anyway, one period of a function. Okay? All right, so this one is cosine squared minus cosine. And we're asked to find the same things we were in the previous problem. Intervals where it's increasing and decreasing. So what is the first step to doing this? What did we do over here? What was our first step? Take the derivative, right? Locating increasing and decreasing, our first step is to take the derivative. So we will find the derivative of f. All right, so cosine squared. And we saw this happen on last exam, I think it was, where we had something squared showed up and we had to take a derivative. When you have a trig function squared, it's not just the derivative of cosine is negative sine, right? What property do we have to use in order to take the derivative here? Either a chain rule or a product rule. The chain rule is a little bit more obvious because we've got something being squared, but you could write it as cosine times cosine, and you could use a product rule too. So it's not that you couldn't do that. I'm going to do it with the chain rule. The chain rule tells me that I'm going to take this power 2 to the front. I'm going to rewrite, and then I need the derivative of cosine, which is negative sine. And then I need the derivative of cosine, right, for the negative cosine part at the end. What's the derivative of cosine? Negative sine. So we'll tidy this up a tiny bit. It doesn't require a whole lot. I'm going to move the negative to the beginning. So I have negative 2 cosine x sine x, and then plus the sine of x. That's the derivative. After I find my derivative, what do I do? What do I do over here?
Find zeros.
Yeah, I find locations where it's 0 or does not exist. Sine and cosine curves do this wonderful oscillating pattern, and they never don't exist, or they always exist, right? I don't have any does not exist locations, so I'm only finding the zeros on this one. All right, so what the grader told me happened on problem number 1 from your quiz was that a lot of you decided to eliminate a variable. You divided by x, okay? And you lost one of your zeros. Be careful. If you have a function and you're trying to isolate pieces of it, you want to make sure that you're factoring as opposed to dividing by something. For example, looking at this, you might say, oh, look, I'll just separate these on two sides of the equation. Okay, it's not necessarily a bad thing. The problem is what you're separating are two pieces that have x in it. If you separate the two pieces that have x in it, the only thing to do from there is to somehow sort of eliminate an x, and we don't want to do that. So anytime both the pieces, or the multiples of pieces, have a variable in them, we're not shifting it to the other side. We're factoring. So what can we factor out of both of these pieces of this trig function?
Sin x.
Sine of x. So I'm going to pull a sine x out in front. That's going to leave me with negative 2 cosine of x, and then what?
1.
Plus 1, yeah. Okay, so just like with algebra, when I get two factors that are multiplied and equal 0, I can set them each individually to be equal to 0. That's a zero product property. The zero product property says that if I have multiplication that equals 0, one of those had to be 0 to begin with. I can't multiply and get 0 unless I started with something that was 0. So we have our sine of x that we can set equal to 0. And we have our negative 2 cosine of x plus 1 that can be equal to 0. All right, so we have to think unit circle. Again, if unit circle is not super familiar to you, you probably should look back at it and start getting familiar with it, because it is going to keep coming up again and again. Sine of x is equal to 0. Okay, so on the unit circle, the sine values are the y values. It's alphabetical. Cosine goes with x, c comes before s, and x comes before y, and then sine goes with y. Okay, so the y values. So where on my unit circle do I have y values that are 0?
Over 2.
Okay, x-axis. You're thinking y-axis. X-axis, actually. Those are my y values of 0, right? So what angle measures am I talking about at those two locations?
0 and 1. Pi.
Okay, 0,
Yeah.
pi, and actually 2 pi since it's within our interval. But to be honest, do you see what this actually says up here? It has to be between, which it actually means it's just pi. We're going to leave it at the 0 and the 2 pi. It's not going to hurt anything. It's sort of going to bound our interval at our endpoints when we are actually doing our sign chart anyway. So leave it, don't leave it. It doesn't really matter. It's not going to affect anything. But we're not going to extend beyond 0 on the left or beyond 2 pi on the right. Okay? All right, negative 2 cosine of x plus 1. So I'll do negative 2 cosine of x is equal to negative 1. And then the cosine of x is equal to 1/2. All right, good? Okay, now zeros are easy to see on the unit circle because you see 0 nicely. 1/2s are not quite as easy. 1/2 values and square root of 3 over 2 values occur at one of two locations. And it depends on whether you're doing the sine and cosine on which one it is. So they either are occurring here or here, and then I'll have the mirror images in all the other three quadrants. This first angle measure has a smaller y value. Like if you look at the y compared to the x, like how far right I am compared to how far up I'm going, the x value is the bigger one, right? X value is bigger. So that means that this is square root of 3 over 2, and this one is 1/2. And when I move up to the next one, it reverses. So this is 1/2, and then this is square root of 3 over 2. I mention it because I don't think, for the most part, you really need to memorize the unit circle. You can reason it out if you need to without having memorized it each time by looking at the dimensions of what's going on. What's bigger? Is x bigger or is y bigger? Oh, well, it's x. Well, that means that the x is the square root of 3 over 2. All right, the sine values are the y values, but this time I'm looking for cosine. So the cosine values are the x values. So which of these two has the x value I'm looking for?
The top one.
The top one, right? The top one. And so that's a good description because we haven't actually described anything further on what that is. So it's this one right here that has the x value that I'm looking for. Okay? Okay, and then you mentioned it, Levi. What's the degree measure?
60.
It is 60 degrees. You're right. But we need that in radians, and so that's pi over 3. Very good. So this is pi over 3. But everything happens in symmetry with the unit circle. If you flip to a quadrant 2 or you flip down to quadrant 4, everything's symmetric. So if I come over to, well, let me actually just make one comment about, let me write this in before I get going any further. So pi over 3 is one option. In the quadrants, quadrant 1, where I am right now, every value is positive, right? X is positive, Y is positive, it's all good. If I flip over to quadrant 2, some of the values become negative. In particular, is it the X values that become negative or the Y values? Yeah, so X is negative over here. And because I'm working with cosine, I am concerned about my X values, because cosine values are X values. I don't have the cosine of X being negative, correct? So I'm not in quadrant 2 to get another 1/2 value. All the X values over there are negative values. So I can get a negative 1/2, but that's not what I'm looking for. I'm looking for positive 1/2. What that means is that reflecting over into quadrant 2 isn't helpful for this problem. If it were sine, it would be, because the sine values are the Y values, and Y values are positive there. So instead of reflecting to the left and into quadrant 2, I need to reflect down into quadrant 4, because that's the other location where my X values are positive. So over here, oh goodness, we're going to reflect down to here. So just as we went up to the top one to get to pi over, or to get to get pi over 3 with the value of 1/2, I need to go down to the furthest bottom one to get the same value. Down here, I will have another location where I have an X value of 1/2 and a Y value of square root 3 over 2. And while it is true that I could go backwards and say, hey, well, up goes positive pi over 3, down goes negative pi over 3, I can't do that here. Why? And why do I have to go all the way around, Levi? You're right.
Because it has to be bigger than 0.
Okay, and what told me that, Ian?
The interval?
Yeah, my interval, I'm going to have to go this way. That yellow is kind of bright, but I need to go around the positive direction because my interval told me to, right? The problem said that I'm supposed to be between 0 and 2 pi. It doesn't allow me to go negatives because the interval was set for me to start with. 5 pi over 3. You're right, it is 5 pi over 3. So this angle, the yellow one I marked, is 5 pi over 3. If you aren't sure, you could count it out, right? So we're at pi over 3, 2 pi over 3, 3 pi over 3. You can count it out like that. You could also go backwards, right? Going all the way around this way is 2 pi, right? If I were to go backwards a little bit, I'd have 2 pi minus pi thirds. And 2 minus 1/3 is 5/3. So you could do it from that perspective too. Of course, your other option is to go back and to memorize it more sort of concretely of just, rote memorization for the unit circle, and that's fine. But you can reason through this if you don't want to memorize, or if memorizing is just something that doesn't work for your brain real well, okay? So these are my two values, pi thirds and 5 pi thirds. Okay. Typically speaking with trig functions, we have to work a little harder to get those angles, right? We have to work a little harder to get our zeros than we do with polynomials. Not always, but often we do. So what does this look like for a sign chart then? Well, we're going to set up our sign chart with these x values. I mentioned that our end caps, if you will, is that we're going to be having to be stuck between 0 and 2 pi. We are because the interval told us to at the beginning. You want to highlight it in purple, right? You can also see there's that 0 and the 2 pi that are showing up from the first value where sine of x is equal to 0. I need the values pi over 3, and 5 pi over 3 on the number line. They don't have to be to scale, but they do need to be in order. So which one comes first? Pi over 3. Which one comes second? Pi. And the third one then would be 5 pi over 3. Okay, so we need to check values in between. I didn't grab a calculator today. I did miss that, so somebody's going to have to help me with the calculator. I'd like to show you how you can use your calculator to do this, where we don't need to depend on the trig values at all to do it. We can just use values that are nice to just plug in, right? Integers or fractions or decimals or something. We don't need pies to work with this. We need to test a value in between these things, right? We need to test something in between 0 and pi thirds, in between pi thirds and 3, and so on. That's what we need to do. So I would like for you to just think about what you know about pi. What is pi approximately? 3.14. We just had Pi Day recently when you were on spring break. Did you know that? March 14th is Pi Day. Yeah, they actually had here on campus pizzas, like pies, pizza pies, in the GC for anybody interested. So you might have seen an email about that. All right, so pi is about 3.14. It's close to 3 anyway, right? It's close to 3. So if you think about taking something that's close to 3 and dividing it by 3, pi over 3 is approximately what?
1.
It's approximately 1. Did somebody just say 15? What in the world? 1. It's approximately 1. Okay. And then the pi here is approximately 3. 5 thirds. What is 5 pi over 3 approximately?
5. Wait.
Is it about 5?
I can agree with 2.
5.
2? It's about 2 pi. It's almost 2 pi. So I think 5 is probably a pretty good estimate. You could let your calculator do it too. Tell me what your calculator says. What's 5 pi over 3? 5 sounds about right to my head. 5.5? Okay, so I'm just going to write down 5.5. Okay. So these are the approximate values, and we want values in between it. So what's approximately going to be somewhere, or what is something that's going to be between 0 and 1? 1/2. So we're going to pick, or I'm going to pick anyway, a value that's between these. This is a little bit too thick of a pen. Let me move this. So I'm going to pick the value right here of 0.5. You can pick anything. 0.5 will be just fine. What is something nice that's between 1 and 3?
2.
2. I like 2. How about between 3 and 5?
What's that?
4. 2 pi is approximately what? I didn't write that one down. Yeah, that one's approximately 6, so this one's about 6. So something between, we could do
0.5. We can do 5 because as that value.
you could do 5.5, or you could even do 6 actually, because 2 pi is going to be 6.28. So either choose, I meant to change my color, trying to be consistent here. Let's try again. You could either choose the 5.5 like you guys said, or you could choose a 6. It doesn't make any difference. This one is approximately 6.3, 6.3-ish, okay? Okay, so grab a calculator, and you're just going to put in not cosine, you're going to put in this your derivative function. So any of the versions of the derivative function that you have, either of these two, you don't need the equals 0 part, but I kind of like the second one of my boxed in piece. Then just put it into y equals. So I'd put in -2 cosine x, sine x plus sine x. And then you can go to your table and you can put in these values, and we put in this sort of a brighter red. This 0.5, 2, 4, and then either 5.5 or 6. And remember, what we're concerned with is the sign that we get. Do we get a positive or do we get a negative? So what sign do we get when we put in 0.5? And negative is correct. There we go. What sign do we get when we put in 2? A positive. How about at 4? Negative. And at 5.5 or 6? Positive. Okay. Now, a lot of times trig functions will oscillate, but a lot of times polynomial functions will oscillate too, but not always. So don't just get the first one and then assume you know the rest of them. It doesn't always work that way. Be very careful. Just check them all. Now, the directions simply ask us to identify where it's increasing and decreasing. So let me shift this up a little bit. Using that sign chart, we'll start with increasing because it actually said that in the directions first. Where is this graph increasing? Okay, pi over 3 to pi. Uh-huh, 5 pi thirds to 2 pi. And where is it decreasing?
0 to pi over 3,
Mm-hmm.
and pi to 5 pi over 3.
Excellent. Any questions on that? Okay, our directions are going to get a bit more involved with our next sets. We're actually going to be finding those maxes and mins.
You go back.
You bet. Sorry about that. Okay. All right, so it wants us to find the critical numbers. That's what we were doing before. Part B says to find the intervals where it's increasing or decreasing. We did that before. The new part C wants us to find the relative extrema. And part D wants us to use the graph to confirm it. And I apologize I didn't grab the calculator, but we'll be able to graph it together even without that. Now, you know what this graph looks like. What is this a graph of? Parabola, opening how? Down. So the graph is going to increase first and decrease second, correct? It will have a maximum, and that maximum will be at what we call the vertex. You know all of that from pre-calculus or college algebra, okay? We're just using calculus to show that the very same thing happens. Now, you might feel like, well, that's sort of silly, but you should really be very happy because it means the problem is pretty quick and easy because the derivative is really easy. So what is the derivative? Negative 4x plus 4. It's still not 15. Negative 4x plus 4. And then what are we going to do? We're going to set it equal to 0, right? This is finding our critical points. What does x equal here? 1. Amazing. Step 1 done, or step A. Okay, so part A, I found a critical point, and there's only one. Part B is to put that critical point on a number line. I only have one of them, which means I only have to test values on either side of 1. What would you like to test before 1?
0.
0. And after 1, we will acquiesce to Ian and we'll test 15. All right. Okay. So we're going to put this into which function? Are we putting it into the original function or the derivative function? The derivative function. We're always putting that into the derivative function. Write it on your paper if you're having a hard time remembering it. Always putting the critical numbers into the derivative function. All right, so if we put the number 0 into the derivative function, do we get a positive or do we get a negative?
Positive.
A positive. And if we put in 15 into the derivative function, do we get a positive or do we get a negative?
Negative.
A negative. Therefore, where is this graph increasing?
In negative infinity up to 1.
And it's decreasing
1 to infinity.
1 to infinity. Okay, and you all love parabolas now in this context, right? They're real quick. The third part here has to do with finding maxes and mins. So I showed you this as we sort of were sort of connecting all the pieces together on that first example last time, that if the graph is positive, it means it's going uphill like this, and if it's negative, it's going downhill like this, which means what's happening right here?
Maximum.
We have a maximum. So on step 3, we can describe that we have a maximum at, and the x value, we know the x value is 1. How can I find the y value?
Get into the original.
Yeah, Josh is right. Plug it into the original equation. Right? The original equation tells us the location that we are in space. So if I put the number 1 into the original equation right up here, what is f of 1? Is it 5? Yep, that's what I have on my paper too. That'll be good. We've got 5 here. So my max is at 1, 5. Now, sometimes WebAssign might just ask for the x value of the max, in which case we wouldn't have needed to find 5. It just depends on the directions that you're given, okay?
Got the comma.
What's that?
You took out the comma. It's 15.
If I do take out the comma, it is a 15. You're really into the number 15 today, aren't you? Okay, all right, we'll see if we can incorporate it somewhere else. If you were to graph this, I'm not going to belabor the point too greatly, but we kind of know what this graph looked like before we started because we already identified it's a parabola, it's opening downward, it has a maximum now we just found at the number 1, and it's up here at 5. So the graph looks something like this, which you would be able to look at a calculator and see that too. And you should be able to confirm it is increasing, and then it is decreasing, and it does have a maximum at that location.
So we just don't write anything for a minimum because there is.
Right. There's no guarantee of having either one on these, actually. So if we have one, we write it down. If we don't have one, we actually will say that there isn't one. Yeah. And in this case, there's not a minimum, so we just don't identify it. Or you could write minimum none. That would be appropriate as well. So if you want to see both of them written each time, you could identify that the minimum is that there's not one. Or you could put D and E for does not exist. That'd be okay. All right, the next question is more interesting because it's a graph you're less familiar with. In fact, you're probably not super familiar with it at all. You know what a cube graph looks like, I bet. A cubed graph looks like this, right? A cube root, that's what this x to the 1/3, a cube root graph looks like this on its side. It looks like it's fallen over, okay? So that's sort of the image we're going to have when we graph this later. And then the +1, of course, just shifts it up 1, moves it up. All right, so the descriptions that we're going to have, or the pieces that we're going to have first is we're going to find the derivative. So what is the derivative of x to the 1/3 plus 1?
Would be a chain rule, right?
Actually, it's not a chain rule. It's just a power rule. If we had something else besides x raised to the 1/3, it would be a chain rule.
1/3 x to the negative 2/3.
Excellent. 1/3 x to the negative 2/3. We want to figure out whether this is equal to 0 or does not exist. Notice I didn't even write that does not exist on the last one because it was parabola. It exists everywhere. This one might be harder for you to see it, but if we rewrite it into a form you're more familiar with, I think you will see it. The 3 is on bottom. The 2/3 being negative is going to push it to the bottom. The third part of the 2/3 makes it a cube root, and the 2 part makes it a squared. Now, it didn't start out in a radical form, so it's not that we turned it into this radical form because we had to from a, matching sort of perspective. We did it because it's easier to identify what we're looking for. At least it is for me. When I look at this in the first form, it's harder for me to decide 0 or does not exist. But when I look at it in this form, it's really easy. Where does this equal 0?
X equals 0.
That's where it doesn't exist. This doesn't really matter, but at x equals 0, it doesn't exist, right? But there isn't any place where it's equal to 0 on top. So this derivative will not equal to 0. There is no place where this derivative is equal to 0, but there is a place where the derivative doesn't exist. So our critical number here is the does not exist category. There, that's what I wanted to do. And it happens at x equals 0. If you misinterpreted it, it won't hurt anything. It's not going to affect your problem. You're going to process it the same way, whether it's 0 because it's 0 or whether it's 0 because it doesn't exist. All right, so that's step 1, part A. Part B is to create a sign chart. So the sign chart has only the number 0 on it, and we'll test numbers on either side. So let's test the number negative 15 and positive 15, just for fun. I'll try this today. Okay, negative 15. That's not what I wanted to do. That's okay. Positive 15. Make it a bit thicker. All right, so if I put in negative 15, where am I putting it into? The original or the derivative? Putting it into the derivative. So again, it's also easier on this one to put this into the derivative location when I'm thinking about the one that I changed into radical form, I think. So if you put in negative 15, what do you end up with? Positives or negatives? Yes. You square it first. So when I square the negative 15, it will become a positive 15 squared. What is that? Is it 625? That's not right. Is it? No. 225. Thank you. 225. I don't know my squared's that high. 225. All right, so it's 225. And then I would take a cube root of 225, which doesn't change the sign. And then I'd multiply it by 3, which doesn't change the sign. And then I'd make that the denominator of something, which also doesn't change the sign. So it is positive. How about positive 15?
Same thing.
Same thing. So that's interesting, right? We have not had that happen before. And it does happen sometimes. The sign didn't change. We can still identify the pieces. Where is this increasing? Everywhere except 0. So we have to identify that. It's negative infinity to 0, and we have to put those parentheses on there, and then we pick back up at 0 to infinity. We can't say negative infinity to infinity because at 0, it doesn't exist. Okay? And if you want to be real explicit, you could write down that the decreasing is that it doesn't ever decrease. There's no places where it decreases. If you leave that off, it's okay too. Okay. Part C is to find maxes and mins. What does this sign chart tell you about that? It doesn't have one. If I were drawing those sort of lines in there, it would look like this. Right? So what's happening at 0? Well, I don't know exactly what's happening, but I know it's not a max or a min. Right? So there are no max, no min. And if we graph this, again, I don't have a calculator to graph for you, but you can graph for your own. The graph you see looks like this. That's terrible. Let's try again. That's not too bad. At x equals 0, let me shift this up here more like that. At x equals 0, we're actually about right here. We're exactly right here. We're at 0, 1. And at this point, we have something that we haven't seen happen before in an actual problem. If I'd drawn it well, like your calculator would draw it better, you actually have a vertical tangent line here. My picture doesn't look very good, but imagine it being far more like this, right? There's actually a vertical tangent line, and that's why the derivative doesn't exist. Vertical tangent lines don't happen very often. But then again, neither do sharp curves, and we saw that happen on a previous one last time, or a couple times ago, I can't remember, where it peaked up and then it went back down. Remember that? They can happen. It just depends on how the function is created. Okay, I think we have one more. Is that true? 2 more? One more. All right, directions are going to change just a little bit. Not a lot, just a little bit. It says to consider the function on the interval 0 to 2 pi. Right? We've got an interval again because there is a sign. We have a trig function going on. So that's the reason the directions have changed. Everything else is actually the same. It says find the open intervals where it's increasing, decreasing. Well, that means I find critical points, even though they didn't list that as a separate step. Right? Going to find critical points, and we're going to find increasing and decreasing. And then I'm going to use that first derivative test to find the maxes and the mins. But I'm going to do all of this on the interval from 0 to 2 pi. Okay, and then I'm going to graph it. All right, so we start with our derivative. What is our derivative of this function?
1 plus 2 cosine x.
Okay, everybody good with that? Fantastic. We set it equal to 0, so I have 2 cosine of x is equal to -1/2. Sorry, it's -1, and then I'm going to divide by 2. So the cosine of x is equal to -1/2. We looked at cosine of x is equal to +1/2 before. So in terms of the unit circle, cosine values are x values. Where are x values negative in our quadrants? In which quadrants? 2 and 3. So my cosine values are negative in 2 and 3, which means I need angle measures that are going to give me values in the third and the second quadrant, right? It's the pi over 3s that we skipped last time, right? It's this one up here. I don't know why that's so thick. Let's make that a bit thinner. Well, that'll do it. 2 pi over 3, like Dylan mentioned, and 4 pi over 3. We skipped 3 pi over 3, because where's 3 pi over 3? Yeah, it's at pi. That's not the one we want, yeah. So this first one here is at 2 pi over 3. And then the one that's all the way over here is at 4 pi over 3. So those are the two angle measures I want for x. Notice again, we're working on one interval from 0 to 2 pi, right? That's our interval. So while that's our interval here, we could have been given an interval just from 0 to pi, and that would have been okay. We would have done the same thing, right? We just wouldn't have the quadrant 3 option here. So we just pay attention to the intervals because they are not always 0 to 2 pi. So these are, and so this one is 2 pi over 3 and 4 pi over 3. So I'll set up my sign chart. I am capping the endpoints. I think it's a really good idea for you to write those in because if you don't, you may forget. And you may tell me something then that's not true that doesn't apply to your problem. So I think it's a good idea to write those in. And then we have our 2 pi thirds and our 4 pi thirds here. And we need values in between, and 15 is not going to cut it. All right, so tell me some number, just a whole number, right, or a fraction between 0 and 2 pi over 3. 1 will work. Some number between 2 pi over 3 and 4 pi over 3. 3 will work. Okay, and if you're wondering how he gets these, just find an approximation for each one of these and find a number in between. Your calculator can do all that for you. It's not a problem. And what's the number between 4 pi over 3 and 2 pi? 5 will work. I like using a whole number of values because they're easier to put into my calculator. That's really it, or even decimals than using pi values. So we're going to put each of these numbers into what equation? The derivative. So I'm going to put in 1, 3, and 5 into the derivative function. And this is the version that I would go with. That's the nice one that we found earlier on. And we want to know the signs. What sign do I get at 1? What do I get at 3?
Negative.
And at 5?
Positive.
Positive. Let me make mention why this works. I mentioned you can pick any number in between this interval, right? Because during that entire interval, the sign will stay the same. It can't change, and it can't change because it doesn't pass through another critical point. So that's why if I choose 5 to put in between 4 pi over 3 and 2 pi over 3, and you choose 6, we're both going to get positives. It's not going to be any different. So it's irrelevant to the choice on that interval. The choice has to actually give me, whatever the choice is, has to actually give me the same sign. So then, where is this increasing?
From 0 to 2 pi over 3 and 4 pi over 3 to 2 pi.
Good. And where is it decreasing?
From 2 pi over 3 to 4 pi over 3.
Sorry, my writing's getting a little tight down here at the bottom, but yeah, increasing as written, decreasing as written. How about maxes and mins? Well, positive means I'm going uphill, negative is down, positive is up. So what happens at 2 pi over 3? I have a max. So I have a max at 2 pi over 3 something. We'll find the something in a minute. Let's just hold off. What happens at 4 pi over 3?
It's a minimum.
It's a minimum. Minimum at 4 pi over 3. And how do I find those corresponding output values, y values over here? Plug it in to the original function. And they're not nice values. These are not going to be nice values, like they sometimes are, because I have a polynomial piece x plus a trig piece sign. So the values themselves are kind of ugly. If you actually put those in, I'll write the first one out and we'll just discuss where it came from. You have 2 pi over 3 because that's coming from the x. And then you have square root 3 over 2 because at that location, while the cosine value is negative 1/2, the sine value is square root 3 over 2. And you have something quite similar on the other one. You have 4 pi over 3, and then you have a negative square root 3 over 2. Yes?
Wouldn't in both cases it just be the square root of 3 since it's 2 sine x and the 2's would cancel out?
Yes, you're right. I have a typo on my notes. Thank you for that. They are square root of 3's over 2's, and then we multiply by the 2. Thanks, you're right. Also worth mentioning is that sometimes WebAssign will let you put a decimal in for this. It usually will tell you how accurate it needs it or wants it to be if a decimal is appropriate. So just sort of be aware of the fact that sometimes it requests that or it allows that. But I'll tell you, if you're doing it on a test, I'm going to want you to keep it exact because you can. You've had the mathematics to be able to do this exactly, and I'll expect to see that. If we were to look at this graph, it's kind of a fun-looking graph. So go ahead and take your calculator and graph this, and then I'll sketch what you have after you've looked at it for a sec.
Graph the original.
The original one, yep. Okay, so a sine graph typically looks like this, correct? Okay, what this does is it takes this and it tilts it on an angle. The angle x, sorry, it's grabbing my axes too, I'll move that back in a minute. So this is not perfect, but you're seeing it shift so that it looks like it's a sine graph going uphill. Now that's not exactly what's happening, but you have that same image or should have that same perspective in mind. So you have something that looks like this, where that's not correct. And it will continue to go up and down, but it does it going up and down on a hill. Can you see that on your graph? So this location here is the 2 pi over 3 for the maximum. And this location here is the 4 pi over 3 for the minimum. And the graph itself would start end to end at the 0 and the 2 pi that you were requesting to have it start and end at, or requested to have it start and end at. Okay. What do we think? Okay. In many cases, these look different, right? So you might get to your homework and feel like, we didn't do one like this. And you're probably right. We're not going to do one like everything you're going to see. But the same features are present throughout. We're finding derivatives. We're setting things equal to 0 does not exist. We're finding the positives and negatives from the derivative graph. And then sometimes we're sketching graphs to support that. Okay?